Hello everyone, welcome back to our channel gsipucmysuru. In this session, we'll be solving some more problems in extension with the last session. In the last session, we solved some of the problems, and today's first problem is an antenna has an impedance of 50 ohms. An unmodulated AM signal produces a current of 4.8 amps. The percentage of modulation is 90. Calculate carrier power, the total power and the sideband power. So this is the 8th problem with extension from the last session. An antenna has an impedance of 50 ohms. So let us denote it as R, which is equal to 50 ohms. An unmodulated AM signal produces a current of 4.8 amps. Unmodulated current anta helidaga, modulated anta helidaga we have to consider it as the total current. Before the modulation process, the current or the voltage or the power will be denoted with a suffix of carrier signal, that is C. So IC is equal to 4.8 amps. The percentage of modulation, that is percentage MA, is equal to 90%. So only MA is equal to 0.9. Calculate the carrier power, that is PC, the total power, that is equal to PT, and the sideband power, which is equal to PLSB or PUSB, or sideband power anta helidrinda PSB is equal to how much anadana nod. So in this problem, an antenna has an impedance, resistance kottidare, total power you have to find out, carrier power and the sideband powers you have to find out for the given value of R and IC. We know that PC is equal to IC square into R. PC, the power relation ನಮಗೆ ಮೂರು ಬೇರೆ ಬೇರೆ ರೀತಿಯಲ್ಲಿ ನಾವು ಡಿಫೈನ್ ಮಾಡಬಹುದು. P is equal to V into I, P is equal to V square divided by R, and P is equal to I square into R. So here we are going to use this I square into R because IC and R is given. So IC value is 4.8 square into R value is 50. So the answer is 1152 watts. So PC is equal to 1152 watts. Next, PC you have found out. Now PT. PT is equal to PC of 1 plus MA square divided by 2. PC you have just found out 1152, 1 plus MA value is 0.9, 0.9 square divided by 2. So the answer will be 1618.56 watts. So PT is equal to 1618.56 watt. So we know PC and PT, then we can easily find out this PSB. We know that the total power will be equal to the carrier power, sum of the carrier power and the sideband power. So PSB is equal to PT minus PC, where PT value is 1618.56, PC value is 1552. So the answer is 466.56 watts. So the sideband power is equal to 466.56 watt for the given value of resistance and the carrier current with the modulation index. So this is how we are going to solve the problems. Now we'll move on to the next problem. What is the power developed in an amplitude modulated wave in a load of 100 ohms? So R is equal to 100 ohms. When the peak voltage of the carrier anta helidre, that is nothing but VC, whose value is given as 100 volts, and the modulation index is 0.5. Modulation index anta helidre MA, whose value is equal to 0.5. What is the power developed in an amplitude modulated wave? Andre you have to find out PT for the given value of R, VC and MA. We are having this formula, PT is equal to PC of 1 plus MA square divided by 2. But we don't know the value of PC, but I told you that PC is equal to Vc square divided by 2R, where Vc is nothing but the peak voltage of the carrier signal. So in place of PC, I can easily write this formula Vc square divided by 2R 1 plus Ma square divided by 2. So Vc value is 100 square divided by 2 into R value is also 100. 1 plus Ma value is 0.5, so 0.5 square divided by 2. So by solving this, we are going to get the answer as 56.25 watts. So the total power is equal to 56.25 watts for the given value of resistance, the carrier power, that is the peak value of the carrier power, and the modulation index. So the problems are simple. You have to identify the parameters given and use the formula accordingly. Now we will move on to the next problem. Till now we solved the problems on the power of an AM signal. Here we are having two more problems on the amplitude modulated signal. So let's start with the first problem. A sinusoidal carrier signal of peak amplitude 5 volts. A sinusoidal carrier signal. So this is Vc whose value is equal to 5 volts and frequency 100 kilohertz. That is, the frequency of the carrier signal is given whose value is 100 kilohertz. Is amplitude modulated by a 5 kilohertz signal. 5 kilohertz signal anta helidaga FM value is given which is equal to 5 kilohertz of peak amplitude 3 volts. So Vm is equal to 3 volts and FM is 5 kilohertz. What is the modulation index? That is Ma is equal to how much? And draw the spectrum of the modulated signal. So spectrum na now draw madbeku. Clear? Now in order to draw the spectrum, we will be having three different components. One is called as the carrier component whose frequency is Fc and amplitude is Vc. And we will be having two sidebands which will be named as FLSB, that is the lower sideband, and the upper sideband whose frequency is FLSB and FUSB, which is equal to Fc minus Fm, and here Fc plus Fm, but the amplitude of these two sidebands are same, that is Ma Vc by 2. Hudalva? So we know Fc and Fm, Vc and Vm. So let us first find out this modulation index. Ma equals Vm divided by Vc, where Vm is given as 3 and Vc is given as 5. So 3 divided by 5 gives me 0.6. I am not having unit for this, so Ma is 0.6. Amplitude of sidebands. Amplitude of sidebands is equal to Ma Vc by 2, where Ma value is 0.6, Vc value is 5 divided by 2 gives me 0.6 into 5 divided by 2, which is equal to 1.5 volts. So this is 1.5 volts, even this is 1.5 volts, whereas this is equal to 5 volts. Clear? Now in order to draw this, we have found out the amplitudes. The only thing which is left is the frequency. So FLSB equals Fc minus Fm, that is 100 kilohertz. 100 kilo na I told you, 100 kilohertz minus 5 kilohertz, which gives me 95 kilo or 95,000 hertz, which is equal to 95 kilohertz. Similarly, FUSB, which will be given by Fc plus Fm, which is 100,000 plus 5,000 gives me 105,000 hertz or 105 kilohertz. So Fc value is 100 kilohertz, Fc minus Fm is 95 kilohertz and Fc plus Fm is 105 kilohertz. This is how you are going to solve the problem. You have to analyze the question what is given. In this question they have directly given the frequencies as well as the amplitude of the two signals, and accordingly find the amplitude and the frequencies of the sideband signals also. Clear? Now we will move on to the last problem of this amplitude modulated signal. A modulating signal 10 sine 2 pi into 10 to the power of 3 t. 10 sine 2 pi into 10 to the power of 3t is used to modulate a carrier signal. So next konuvanta equation, that is the carrier signal equation, whereas this is the equation of a modulating signal, is used to modulate a carrier signal 20 sine 2 pi into 10 to the power of 4t. Find the modulation index, that is MA, percentage modulation, that is percentage MA. Find the frequency of the sideband component FLSB, FUSB, and their amplitudes of sidebands, bandwidth of a modulated signal. So these things you have to find out for the given value of these two equations, for the given equations of a modulating signal and a carrier signal. So we know that this is nothing but Vc sine 2 pi Fm, Vm sine 2 pi Fm t, and this is Vc sine 2 pi Fct. When you are going to compare these two equations, this and this equation, we can clearly write that Vm value is equal to 10 volts, Vc value is equal to 20 volts, and Fm is 10 to the power of 3 hertz, whereas Fc is 10 to the power of 4 hertz. Now you have to find out Ma first. Ma is equal to Vm divided by Vc, where Vm value is 10, Vc value is 20, so I will be left with 0.5. Ma is 0.5, whereas percentage Ma is 0.5 into 100, which gives me 50%. So these two are calculated. Now FLSB equals Fc minus Fm, which gives me Fc value is 10,000, that is 10 to the power of 4, minus Fm value is 1000 hertz. So FLSB equals 9000 hertz or 9 kilohertz. Now FUSB equals Fc plus Fm, which is equal to 10,000 minus 1000, which gives me plus 1000, which gives me 11,000 hertz or 11 kilohertz. So FLSB, FUSB ಕಂಡಿಡಿದಾಯಿತು. Now we have to find out the amplitudes of the sideband. So amplitudes of sideband is equal to Ma into Vc divided by 2, where Ma value is 0.5, Vc value is 20 divided by 2, which gives me 5 volts. And the last one, bandwidth is equal to 2 times of Fm, 2 into Fm value is 1000, that is 10 to the power of 3 hertz. So bandwidth is equal to 2 kilohertz. So this is the simple problem. So till now the problems what we solved covers all types of topics of the amplitude modulated signal and the power relation of a AM wave. Now we will move on to the next topic. So the next topic is modulation by several sine waves. Usually the carrier signal containing only one modulating signal is rarely used. That is, modulating a modulating signal with a carrier signal, only one modulating signal with a carrier signal is rarely used. Instead, several modulating signals will be combined with a single carrier signal which just acts as a vehicle to carry the information from one place to another place. But one thing what you have to make sure is the different or the several modulating signals what you are using to modulate with only one carrier signal, adradu frequency bere bere irbeku. That is, you can use a single carrier signal to modulate a several modulating signal whose frequencies are different. By doing this, we can use a same channel through which you can transmit a number of signals together. That is, if you are going to consider an example of a simple mobile phone. Our mobile phones is having a capability to capture the radio signal whose frequencies will differ like 90.8 or 92.7, 93.5. Ithara bere frequencies of the signals, but the carrier signal will be the same. So, the total modulation index of this carrier signal, which is combined with a number of modulating signal whose frequencies are different, will be denoted by MT. So, the total modulation index can be easily calculated using this formula M1 square plus M2 square plus M3 square so on up to Mn square for n number of modulating signals, where M1, M2, M3, M4 are nothing but the modulation index of the several sinusoidal signals or the modulating signals which we are combining with the carrier signal. You have to make sure that this total modulation index value will also lie within the range of 0 to 1. If the value of this MT is more than 1, then it will lead to what is called as over modulation, which contains a lot of distortion, a lot of noise signals will be present along with the actual signal. So, instead of sending only a single modulating signal with only one carrier signal, we can combine a number of modulating signals whose frequencies are different with only one carrier signal. So, the total modulation index will be denoted by MT. So, modulation by several sine waves is most generally used in today's science and technology. So, the next topic is types of amplitude modulation. The frequency spectrum is limited for different applications. That too, for communication purpose, the frequency spectrum is very small. So, we have to make sure that the bandwidth of the signal what we are using to transmit or what we are transmitting from one place to another place, that must be as minimum as possible. So, in order to do this, we are having different types of modulation, that is amplitude modulation. But the bandwidth of any signal can be calculated using the formula 2Fm, where Fm is nothing but the frequency of a modulating signal. Depending upon that, the bandwidth of the signal will vary. But one thing what you have to notice here is only 33% of the total power what you are transmitting is utilized by the information what is being transferred from one place to another place. The remaining 67% of the total power is just a waste which is not carrying any kind of information. That is, the information is present only in the sidebands, which is having a total percentage of only 33%. That is, total power nully only 33% of the power will be utilized by the sidebands which contains the information, and the remaining 67% is just a waste which does not contain any kind of information. So, what we are going to do is we will come up with different types of amplitude modulation, where we will be trying to minimize this 67%. That is, what is getting waste, that waste will be minimized to a larger extent and the efficiency of the signal will become more. So, now let us see the different types of amplitude modulation. Before looking into the types of modulation, that is types of amplitude modulation, one more thing what you have to consider is, in the amplitude modulated signal, we will be getting the modulated signal like this, which is which contains two separate sidebands, which is the mirror image of the other. I will be having three different components. One will be called as the carrier component, and the other two will be called as the lower sideband component and the upper sideband component. But here in this particular amplitude modulation, this and this are the mirror images of each other. So both the contains the information which is to be transmitted, but if I am going to suppress one of the sideband and transmit only one of the sideband, then the maximum amount of power can be saved. The maximum power can be saved anta helidre, I just told you that 67% of the total power is just getting waste, which does not contain any kind of information. So we will be trying to reduce that 67% to a maximum number. Eshtu kadme agutho ashtu percentage ge ನಾವು reduce ಮಾಡ್ತಾ ಹೋದಷ್ಟು the total overall efficiency of the amplitude modulation ಏನಾಗುತ್ತೆ increase ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So in this aspect we are going to classify our amplitude modulation, that is types of amplitude modulation. The very first type of amplitude modulation is double sideband suppressed carrier, that is DSB, double sideband suppressed carrier. I already told you that we will be having three different components. One is the carrier component and the other two are nothing but the sideband components. Double sideband suppressed carrier. We know that this carrier component does not contain any kind of information, but it is just acting like a vehicle to transmit the signal from one place to another place. So in order to increase the overall efficiency of the system, or in order to reduce the loss of power, what we are going to do is we are going to suppress the carrier power and retain only the sideband component. We are just going to transmit the two sideband components by suppressing this carrier component. By doing this, we will be able to save 2/3 of the total power. So 2/3 of the total power, that is for maximum modulation process, that is for MA is equal to 1, I told you that only 1/3 of the total power will be utilized, out of which 2/3 of the total power will just go on waste, which is consumed by this carrier component. But when I am suppressing this carrier component, 2/3 of the total power will be saved, which can be used for strengthening these sideband signals only, such that the information can be transmitted to a much more longer distance. So double sideband suppressed carrier anta helidre, we are going to suppress the carrier component which does not contain any kind of information, but we are going to retain the two sideband signals, and that sideband signals will be transmitted over longer distance. By doing this, the overall efficiency of the amplitude modulated signal will be increased and the power loss can be minimized to a larger extent. Now we will move on to the next type of amplitude modulation. Single sideband transmitted carrier. So here single sideband SSB-TC, single sideband transmitted carrier anta helidre, out of three components I am just going to suppress only one of the sideband and transmit one sideband component and one carrier component. Single sideband transmitted carrier, along with the carrier I am going to transmit only a single sideband component, where the other sideband component will be suppressed. I told you that the carrier component contains 2/3 of the total power and 1/3 of the total power will be consumed by both of the sidebands, but here I am suppressing only one sideband anta helidaga, half of this, that is equal to 1/6 of the total power will be consumed by one of the sideband and the remaining 1/3 will be consumed by the other sideband. But here we are suppressing this single sideband anta helidaga 1/6 of the total power will be saved in this particular modulation process, that is single sideband transmitted carrier. We are going to suppress only one sideband and transmit one sideband along with one carrier component. Clear? By doing this, we will be saving 1/6 of the total power. The last type of this amplitude modulation process is single sideband suppressed carrier. Single sideband suppressed carrier, which is most widely used. Single sideband suppressed carrier, and this is the most widely used type of amplitude modulation. Here what we are going to do is, out of these three components, we are going to suppress carrier component and one of the sideband component, and we will be sending only one sideband component. By doing this, a major amount of the total power will be saved instead of getting wasted. So I told you that 2/3 of the total power will be consumed by the carrier component, and 1/3 of the power will be consumed by two of the sidebands. So 1/6 is 6th of the power of the total power will be consumed by one of the sideband, plus 2/3 by what? The carrier component. So if I am going to add these, I will be getting 6 in LCM tagidre 1 plus 3 2s are 2 2s are 4. 5/6 amount of the total power will be saved by using this single sideband suppressed carrier. So in this last method, a major amount of total power will be consumed compared to other two types of amplitude modulation process. So these are the three different types of amplitude modulation process, that is double sideband suppressed carrier, which will be denoted by DSBSC. Second one is single sideband transmitted carrier, which will be denoted by SSBTC, and the last one is single sideband suppressed carrier, which will be denoted by SSBSC. Out of these three, the last one, that is the single sideband suppressed carrier, is the most widely used type of amplitude modulation. But coming to the application and advantages and disadvantages of this SSB-SC and ಹೇಳಿದಾಗ, this SSB-SC is most widely used for telemetry, mobile and landline communication system, military communication, navigation, point to point speech communication. ಈ ಥರ ಬೇಕಾದಷ್ಟು applications are present for this SSB-SC. Coming to the disadvantages of this SSB-SC ಅಂತ ಹೇಳಿದಾಗ, we need a complex circuit in order to suppress both the carrier signal as well as the one sideband component. A complex circuit illa anta helidre, it is not that easy to suppress that one sideband component and one carrier component. Disadvantages anta helidaga kadme ide compared to advantages. Advantages nalli we will be saving a large amount of power and noise interference kadme irutte. Power supply what we are going to use is very very small, and the bandwidth of the signal decreases. So overall bandwidth ಏನಿದೆಯೋ ಆ bandwidth ನಲ್ಲಿ ನನಗೆ ಜಾಸ್ತಿ stations na ನಾವು accommodate ಮಾಡಬಹುದು. This type we have already solved one problem. So bandwidth ಕಡಿಮೆ, single station ದ bandwidth ಕಡಿಮೆ ಆಗ್ತಾ ಹೋದಷ್ಟು overall communication system ನಲ್ಲಿ ಇರುವಂತ bandwidth ನಲ್ಲಿ as many number of stations can be easily accommodated. So these are some of the advantages of this SSB-SC. So with this, let me conclude this session at this point. I'll be coming soon with the next video. Until then, take care. Bye bye.